Good afternoon. Good afternoon. I'm going to tell you about next week's speaker. His real name is Nat Ciglio, but actually I pronounce it in the English way, Ciglio. Nat Ciglio on X-ray diffraction, and this is going to be an open forum. It was a forum that was selected by my predecessor, and this is why I have trouble pronouncing the speaker's name. I'm sure he knows what is the correct version. In 2 weeks, we will have a very close forum by Ron Ryder, who will, yes, he will talk about distributed document architecture. At least that's what he told me in the gym the other day. Now, I cannot possibly match Danny's suave eloquence or his rapier wit, so I will not introduce him officially. There is no need because everyone here knows that he's the current president of AAAI. He has been at PARC since 1972, which makes him almost a founding father, and that his PhD is from MIT, but he also has Harvard and Rensselaer in his background. We also know that he's an RS, meaning a research fellow. In our author file, his dossier enormous. I mean, his papers and his honors are so many that we had to split his file into 3 separate files. I checked it today, and I was almost as impressed as when I saw Danny mentioned in the New Yorker. Then.
Thank you, Juliana. Well, it's fun to be here today. The talk I'm going to give you today was originally prepared for an audience mostly of people in the AI field. It was really my opportunity as president of AAAI to think back where artificial intelligence has been and where it might be going. And I realized as I was doing this that in fact AI was not alone. And so a lot of the things that I'm going to talk about today are not artificial intelligence, but things that I've learned about around here which affect my view of artificial intelligence and where artificial intelligence needs to go in a much broader context. Now, when I think back to when I started, which is very difficult, we were just discovering that if you programmed computers to manipulate symbols and you interpreted the input and output correctly, you could get people to believe that they were doing things that were intelligent. And so we manipulated a lot of symbols and did a lot of intelligent interpretation. And we're very excited about where we thought we were going. And we would use terms like, well, the computer knows this and the computer knows that, and this kind of terminology was rampant, and we got in lots of trouble with the press. And it was only about 1980 that we started understanding a little bit about how to separate some notion of what knowledge is from all these manipulation of symbols that we've done. And let's see. And that was because Al Newell, who was the, we can turn down some of the lights that are up here. We don't need, maybe make it a little clearer. Al Newell gave a talk as the first president of the AAAI. And what he did in that first talk was to talk about something he called the knowledge level. And the idea of behind the knowledge level was to be able to sort of sort out the difference between the implementation of your systems and this whole conception of what the system might be said to know. So he defined the notion of rational behavior, and basically he talked about how could you say that a system knew something. Suppose we had a system perhaps called Danny, and it had something you might define as a set of goals and a set of knowledge. the principle of rationality basically said you could say an agent was acting rationally if, in fact, it was following, using the knowledge it had, it was trying to achieve its goals. And in some sense, what he did then was to formalize the current practice, where people would write some specifications down. Often they'd directly put it into symbols, but in fact, the specification was different than what was in the symbol level. So this was a very nice way of starting to think about these agents, these single minds, so to speak, these computational minds, in isolation and talk about what they knew. But when I was starting to think about where we were now, I realized that this notion of the single mind, you know, the deaf, dumb, paraplegic mind out there was really the wrong way to be thinking. And that many of the things that were happening nowadays had to do with the interaction of agents, several agents trying to achieve a goal together, the interaction of agents with the world. And so my goal in sort of thinking this thing through was to say, could we get a description of interacting systems in the same way that Newell got a description of single agents, which was independent in some ways? Can we define a description at that level? So I try to look at issues that came up in understanding these kinds of interactions in systems. And when I try to formalize this as a level, I found that that was a real problem, because the kinds of assumptions that you wanted to make about the elements of the interaction were too diverse. So I couldn't get a single level that would define this thing. But I did manage to come up with a set of characteristics that cut across many interacting systems. And so in order to illustrate that it cuts across these things, I've taken examples from many places: psychology, sociology, AI even, and try to show how these same kinds of issues occur in many different systems. And you'll see that I've actually been strongly affected by the environment that's around here, because there are many examples that have been pulled out of work at Xerox. So the 5 issues I'm going to use for my organization. Let's see, does this actually work? Oh, good. We had a battery problem before. The 5 issues that I'm going to use to organize my talk are: first, common grounding. If you have 2 agents working together, they're going to communicate at all, they have to have some notion of a common ground. They have to have something in common. And I want to talk about what does it mean to have that in common, and what does it mean to keep something in common. Now, sometimes 2 agents can't work well together. They don't have that common ground. And so you have to do something to match impedance between these agents. Now, suppose you have these agents already working together, and they have their impedance matched. Well, then how do they allocate resources? So the next kind of issue that comes up when you're talking about agents working together is, who's going to get what resources to do the job? Well, I said the job. Well, there's an issue when you have many agents, and especially when those agents, say, like people, have many different goals. How do you get them to coordinate, to come together and get a single thing done? And finally, how does that single thing that you want done fit into a work practice, which is a much larger context? So I want to talk about these 5 issues, and end with kind of a challenge for where I think we ought to be going, what kind of criteria we ought to be using for the future. So common grounding. You'll see a lot of cartoons from the New Yorker in this. And this is one of my favorites. It illustrates the problem of what happens if you don't have common ground. I mean, she's not quite communicating what her idea is to all of these other compatriots. Now, maybe in this situation it doesn't really make a difference, but in situations in which you'd really like to get something done, it does. Now, one of the things I'm going to do in this talk is I'm going to sort of contrast the situation with a very, where you have a simple assumption with what the real world is like. So for example, the simple assumption is that all the communicating agents are constructed with a complete common language. So you don't have to worry about it. That what one agent means is exactly what the other agent interprets. So for example, the standard expert system stereotype, you have the expert having put together a system, and then that expert interprets the symbols that are coming in and out of that system. Well, that's not quite the way it really works. And what we would like to do is look at what the issues are in getting a common ground where this common ground can be groundable in the world. I mean, these symbols are about something, as one of the people around here usually says. And we want it to be extensible and sufficient for the task, though it doesn't have to be complete. That is, you don't necessarily have to have a complete understanding of other people or other agents. So let me start by talking about people and how they build common ground. Here's a little experiment that was done by Herb Clark over at Stanford with a number of others. And here are these things they call tangrams. And there were two people, one a director and one a listener. And the director had a set of cards with these tangrams on it. And what the director had to do was to tell the listener over here what it is, the order in which those tangrams were on those cards, so that the listener could then rearrange his or her set of cards in the same order. So that was the job here, but neither of them, they had no common visual perception. So they had to use a common ground that was based in their current knowledge of the world. Now, they did this 6 times, and they got feedback on this task. They reversed roles, too. The director became the listener. And what happened? Well, they used phrases which describe these things in terms of, the skater with his foot out. These were phrases that come from their common experience, but soon they reduced the size of the phrase, and sometimes they used the common experience of building this or doing this task to actually help them. And what happens is people get very much better. The number of words they need per reference went down dramatically each time. And they use all these kinds of tricks, what they said last time, the kinds of mistakes they made, the kinds of confusions they had. So that's just talking about what it is that people do. People have conversational interaction where both the speaker and the listener take some responsibility for building the common ground. Now, let's talk about a different kind of common ground. Here's an expert systems problem. The Eaton Company has a large fleet of trucks. One of the things they have to do is they have to balance the wheels of these trucks. Not balance the wheels, but balance the brakes. Because if the brakes are not balanced, then the back of the truck will stop slower than the front of the truck, and the truck drivers get very angry. So they have built lots of tools to help them with this. So they have something which measures lots of things about the dynamics of the wheel. And what they do is they get all these graphs out, and they have a few people who are really good at interpreting these graphs, these experts, and they say, okay, tighten up the right front or whatever. Well, they didn't have very many of these experts, and it's kind of hard to ship the trucks around to where the expert is, and the expert didn't want to travel nearly so much. So they decided to build an expert system. But this expert system couldn't just have symbols in and symbols out. That wasn't enough, not to have a real common ground. So what they did is they built something which would interpret pieces of the world and transform the pieces of the world, something like these graphs, into words which the expert could understand. And then the knowledge-based system that they built and the expert had a common ground in the world because the expert trained this perceptual system to get that. And then that allowed a rule-structured knowledge-based system to be used for helping in this task. And that made it a lot easier to transfer the knowledge because the common ground was transferred through this medium. Let me talk about a different kind of problem. The problem here that I'm going to talk about is one that's facing lots of people in the knowledge representation community. You'd think that people in the knowledge representation community, since there's internet representing knowledge, would all understand what that meant. But of course, it's just the opposite. If you're in such a community, you're really trying to understand what it means to have knowledge, and you have your own way of having it. So what's the solution if you want to share this knowledge? Well, a solution that's being attempted right now is to build an interlingua, something which is at least a common ground over some small part. And if you want to do that, you can't just have an interlingua which is fixed. You have to have some way of extending the base vocabulary. And so there's some ways of defining new primitive concepts, like a person is something which at least is a mammal, or a man is a person with sex equal male. That's a definition.
Then what is KR?
Knowledge representation. Sorry. But now, if you're talking about knowledge representation, you're really talking about reasoning. And so it's not enough to simply give new verbal definitions, but you also want to talk about different processes that are going on in the language. So there's a question about how do you talk about those processes. So in this particular case, they wanted to define something like, what is default reasoning? Default reasoning is, if I know that all birds can fly and Tweety is a bird, do I assume that Tweety can fly? Well, if Tweety is an ordinary bird, yes. If Tweety is a penguin or is a duck that's been cooked, or any of the other kinds of ways that that birds might not be able to fly, you don't want to. So how do you talk about this? How do you talk about this process in the language? Well, the way you talk about it is you define the kinds of reasoning that goes on by talking about the results of that reasoning. The proofs are sequences of sentences, and languages can be described in proofs. And then what you can use is the reasoning system to reason about these proofs. So you can say, well, arguments which are shorter are preferred to arguments that are longer, or arguments which don't use assumptions are better than arguments that do use assumptions. So what happened there is there's a notion of reification, that is making real, making an object out of pieces of the process, and then allowing the system to work over those objects. So it's a kind of reasoning process using those objects. And so that's a principle that we've seen around a lot, allow the full language to be used here. We try to do some of the same thing in the Common Lisp object system. Brian Smith has been talking for many years about different ways of making things real and what it means to be able to manipulate them, this reification. And so this kind of thing is now part of what we need to do in order to sort of extend our common ground. Well, there's lots more to be said about that, but let me go on to the second case. Here the question is, what happens if there isn't a common ground? What if things don't quite fit? This says, I don't know whether you can read this back there, with proper diet, moderate but consistent exercise, and the development of a healthy mindset, I should be able to fit in fine. Well, I've often felt that way. What do you do about things like that? Where do these things come up? I mean, the simple assumption in computer systems is that everything is changeable. I was talking to Stu about this, and he says, well, you don't always have to put in a mediator. He says sometimes you can change your users or train them. But I thought that was not what I wanted to make as a point here, so I'm going to talk about putting mediators in between. And there's lots of reasons to put mediators in between. One of the earliest versions I know of a mediator being used for a useful purpose was some work done by Tom Sheridan at MIT. And what he had was a remote manipulator, and that, when I say remote, he was planning on having this be under the ocean or maybe up on the moon. And the problem is that you couldn't get very good communication. And even if you could, the person who was going to control the device couldn't talk the right language to really control it, because the device, which was simple, knew things like set the joint to a certain position and joint angle. So he put in the middle a kind of supervisory monitor. And that had a number of roles and a number of implications. It, first of all, did this language translation here. So you went from languages which were task-based to languages, the language here, which is in fact implementation-based. It also meant that there could be, given these three agents, a division of labor. So you might have filter and servo tasks here, skill-based tasks, which you need to have very close to the place where things are happening. You could have some planning and monitoring going on in this mediator, and then the human could, in this case, think about the tasks they wanted to do and use the knowledge. Another very interesting use of the mediator notion is some work that was been done here by George Robertson and Stu Card and Jacques McKinley. Here the issue is what happens when you're watching your computer screen and you want to watch what's going on in a fairly complicated environment where there are many agents, and the task that they chose was an information technology manipulation task, going out to find various information that you needed. And what they wanted to do was to put something in between which allowed the human to make better use of his or her capabilities without putting a lot of burden on the task agents. So there was issues of matching the time scale, monitoring the activity, being able to say, turn that off even though that wasn't ready to be turned off, transforming the language. And the basic notion here, one of the important notions I think that came out of it, is moving cognitive load to perceptual load, changing the processing that was going on. And this is an example that comes from their work, in which you've seen this, you've probably noticed what this map is. This is a map of at least part of PARC. And it turns out it's a lot easier for you to follow this arrow from my picture to this place down here and interpret where I might be, or at least where my office is, than it is for you to do this kind of thing by trying to say, where is 1640 mumble? So this kind of movement from cognitive to perceptual processing is something that a mediator can help with. Gio Wiederholt over at Stanford has talked about having mediators as a basis for a large-scale distributed knowledge-based system where there's lots and lots of knowledge bases, say, all on a network. And what you want to do is have a mediator which can transform what that knowledge base looks like to any user based on the task that that user wants to have. So, for example, if you want to change the kind of language, there's, going from social security number in a database to the person's name, because that's what we like to deal with. Or be able to use the notion of excessive pay, where to the IRS, excessive pay means one thing, like you got paid too much for your move, versus the board of directors, who might think that you got too much for the amount that you put into the company. There's also notions of composition of events. Con Edison, here's a scary story for you. Con Edison actually uses artificial intelligence systems to help in the control of the electric power system in the Bronx in Manhattan. And I'm visiting there sometime soon. What it does is it actually is an intelligent filter. At their control center for all this electric power, they get in something over 100,000 interrupts a day. 100,000 messages that say something's wrong. And the problem is that the 10 or 11 people who are processing these things get lots of these things, and they say, what? And part of the problem is they get the same thing over and over again, and they can't just say, I know, I know. So part of what they're doing is they're shifting some of the load of processing these things, making them go from what the system can tell to what the humans want to see. And I think that's a kind of thing that you want to see when you have a mediator. Now that we have everybody working together, I said we should do some resource management. And here you see an alternative form of resource management with the whole scout troop is telling the scoutmaster exactly how to go. It's much easier to manage resources if there's only one person at the wheel, I guess. So what we want to do is assign resources to tasks, and we want to find appropriate agents. And the simple assumption that you might make is that there is one agent who's both omnipotent and omniscient. And although that was good about 2,000 years ago, it's not quite so good anymore. So how can we think about this? Well, there's lots of models for thinking about this. And one model has been developed here by Karl Waltzberger and Bernardo Huberman. And they said, well, what if we used a market metaphor? And in the market metaphor, what they were thinking about is just a network of processors, and what we would like to do is sort of keep that network of processors busy. And what the processors would do is say, I have some free time now, and they broadcast that around. And what you'd like to do is have each of the processors that have something they want done bid on that time so that they can, the one that has the most resources or thinks it's the most valuable actually gets that resource. An interesting thing is you might think, well, we should have a bid and we'll keep going to the highest bidder, but that would have too much communication in it. So one of the things they did is they used a sealed Dutch auction bid. And what that is you get one bid, and the winner is the one who bids the most. But the price paid is the price that the second bidder did. Now that means that if only one person, or one agent wants some resource, then they don't have to pay anything for it. But if there's many people, then what you're doing is you're sort of keeping the price at sort of where the right bidding level is. And it turns out that's a very efficient thing. I found that an interesting fillip on the whole market system. And what happens? Well, what happens is for 10 to 20 processors, there's very quick convergence. The processors all get about the same amount of resource utilization. And you get linear speed up here with some overhead for communication. But when it gets to be about more than 15, 20 processors, as if you get to a group that's more than about 15 or 20 people, things get a little chaotic. What you do is you see a lot of variance in what the processor load is. This comes from the fact that there's delay in the communication. And so a processor says, I have some free time, and then that gets to another processor a lot later, and they say, okay, I got something for you. But it's too late. That one is now backed up by a certain, too much. So one way to get out of that kind of bind is to say, well, look, we can't just have everybody talk to everybody. What we'll do is we'll have a hierarchical model. And so Eric Loomer and Bernardo went and looked at what it would mean to do some hierarchical rates of communication. And they found out that if you had a hierarchy now, and you had the groups sort of communicate among themselves at a fairly fast rate, but other groups at a slower rate, what you'd get is very quick kind of load balancing and convergence, and it was kind of nice up to about 300 or 400 processors, and then of course things start to break down again. This is too much communication. And in particular, they break down even smaller if there's delay in the system, like if you actually build a hierarchy like this, and the way you do your communication is through the hierarchy, and there's some delay, then things break down fairly quickly. And what you get is problems like this, where you get the groups converging, but the groups' interaction will have this kind of oscillatory behavior, and they believe even some chaotic behavior. Well, that was kind of depressing to think that there was no way of doing things, but they came up with this very clever thing which, you know, seems to have at least a moral to me, if not. And that is, if there were a few people, few agents, that had informal links with people in other groups, then, and they communicated, so there was these kind of lateral links, that informal communication made for a lot more stability here. And Bernardo has claimed private communication, that that's probably why it's actually useful sometimes to have a reorganization, because it keeps some of those links in place. But it really talks about the fact that, that you can see how the informal links, how the organizational structure can help in this very simple model. Well, we're talking about resources. One kind of resource that has been ignored a lot, or certainly was ignored a lot in AI, was the world as a knowledge resource. I mean, after all, I don't have to remember exactly where I put that pointer down. That is the exact location there. I just remember it's on this thing, and if I want to go get it, I can pick it up. Because I know that when I go over there, I'll be able to look and see. So I don't have to remember things nearly as well. So the world is very nice in that it usually stays fairly stable. So, for example, you can remember a path the way these people do. And hopefully this parking lot is better than the woods where Hansel and Gretel did it. You can also change the world and use it for a memory prosthesis. I mean, that's what we do when we make lists, or leave marks from where we've been. And people have been looking at that same kind of thing inside of computer systems. They've also been looking inside of computer systems to see how interacting with the world can save in processing. So, for example, rather than having to do lots more processing to determine what is that 3D object, which is the object and which is not, you might move your head or your sensors, because in fact objects tend to move together as a unit when you move around. Or you might actually generate some external symbol structures. Probably too often I have to listen to what I've said to understand what I really meant, and then fix it, of course. And finally, I was talking to some people who build simulators, and they say the hardest thing about a simulator is not to get it to do the right thing. It's to get it to not do the wrong thing. And there's all these constraints that otherwise you just don't think about in the world. And the nice thing about trying things out in the world is the world doesn't do impossible things, I hope. Well, what about agents as resources? Will these agents change as they're used? Well, let me give you an example from a very different field. When you have bees, when a queen bee sets up a hive with just a few workers, the queen can do anything in that situation. In fact, there's no caste system at all. And the workers work there. But as soon as there starts to be enough workers there, then the workers take on fixed roles, and there's a fairly strong caste system. So those who are the foragers go out and look for the honey, and those who are the hive workers are building the hive. Except that the world isn't constant. And so sometimes in the early spring, there may be lots of flowers out there to go gather the honey. And so they need lots of workers to put the honey away and put the pollen away. Later on, when the flowers have started to die out, the foragers need to go out further. And there's a very, very simple feedback system which actually changes the caste system. If the workers have to wait around too long waiting for somebody to come back from foraging, then after some amount of time, they actually become foragers, and some of them go out. Now, do we see the same kinds of things in our computer systems? Well, one example that we have is there was a system called Enterprise that was done by Tom Malone and Richard Fikes here at PARC. Both of them were here at PARC. And it was a system in which computers would bid for work. That is, unlike the system I described before, where computers would simply say, "I'm free," these would be somebody who wanted a job done would say, "Here's a printing job I want." And the computers would each say, "I can do that printing job." And what happened is some of the jobs were compilation, some of the jobs were printing, and if the computer had done the compilation job just immediately before, it had the compiler code loaded. And what that meant was it was faster at doing the compilation. And the printer, when it had done the printing, had all the fonts loaded. It was faster at doing the printing. And so you saw this specialization, but again, there was kinds of adjustments for the kind of jobs that go on. And that seems like a very useful thing to have. Well, if we have agents who do different things, how are we going to find them? And Mark Stefik, in a very nice paper on the knowledge medium, talked about what would happen if you had a knowledge market out there. In addition to all those people who have knowledge and who can do tasks, there's lots of roles that are still need to be fulfilled. Although many of us sort of say publishers, they give us a hard time. In fact, publishers do an awful lot. They do filtering, they do formatting to make sure things are in a common way. They do the distribution. And there's lots of other roles for people in and agents in this knowledge market. And to the extent that we have an interactive system, we're going to need those kind of roles filled in order to be able to get a true knowledge market that will work well for us. Well, we've talked about the resources, but now let's talk a little bit about the coordination of goals and actions. We see that this is an example, a counterexample of coordination. The simple assumption is there's this central creation of problem-solving agents. And they're focused on a single goal, and the agents are associated with such a goal. And there's kind of minimal interaction among the agents. And there's no learning. I mean, what one agent learns isn't learned by another, and they don't learn very much because they can't take it back because their agents are created. So the problem here is that you can't communicate, you can't learn, you can't have learning from different situations. Well, one way of getting coordination is through a shared artifact, and one shared artifact that is being built now inside of Xerox, something called the Component Selection Advisor. And the problem that it's trying to solve is the following. Right now, when engineers start doing some engineering design, they do the design, they finally get things done, they have minimized the unit manufacturing cost, and then they pass it over to manufacturing. Manufacturing says, can't quite do it that way. So they send it back and the engineers fix it up. And then this kind of sequential design goes on and eventually gets down to procurement. Procurement says 24.8 volt motors take about 6 months instead of only a month to get those things. So what's being put together here is something which will communicate with all the people involved in the production of a product, so that procurement can say, these are the things that are simpler, these are the things that our best suppliers can give us. Manufacturing can look at the design and say something about whether it's useful very early on. The Component Selection Advisor itself can, in fact, provide that knowledge and be a medium for that knowledge to be transmitted to the engineer. What about computer systems that can help people coordinate? Well, a system put together by Terry Winograd and Fernando Flores called the Coordinator is trying to do this by providing a semi-formal system which deals with what they think is the basic premise of coordination, namely requests by people and responses by others about those requests. So you might respond, for example, by promising to do something that your boss said, or you might respond by declining to do it, or you might make a counteroffer. And having this kind of set of things that are there, the system itself can actually understand parts of this. It can understand the respond by date, it can understand the complete by date, it can understand the notion of an alert, but it doesn't have to understand the notion of a need. And people can organize their lives in terms of the things that they've promised and trying to understand what they've promised to other people, what they have been promised, and be able to have this set of continuing conversations where they can use the tool to organize that set of conversations. Well, if we're going to have a notion of commitment, one of the basic premises of artificial intelligence is if you're going to use some concept, you should try and understand it, represent it. And so the notion of what is commitment and intention is a problem that's been worked on by Phil Cohn and Hector Levesque. And they have a very interesting way of sort of formalizing this thing. Let me try and illustrate some of the problems they're trying to solve. They want to get something, suppose I have a robot, Robbie the robot, and it's supposed to be a robot that understands about intending to do things. And I ask it to go in the other room and get me a beer. And Robbie goes off to the kitchen to get me a beer, and about an hour later, I go into the kitchen and Robbie's doing the dishes. And I said, "What happened to my beer?" Robbie said, "Well, I decided doing the dishes was more important." I would send that robot back to the factory. Well, the next one that comes back might do it, and I say, "Oh, get me a beer." And it goes into the kitchen, gets me a beer. I take the beer and say thank you, and it goes back in the kitchen, gets me a beer. And then, having recognized this from Fantasia, I send that one back. And then the next one they say, I say, "Go get me a beer," and it goes out to the kitchen, and then I go out to find out where it is, and now I see it out in the street, walking down there, and it's 2 o'clock in the morning, and well, it didn't recognize how much I might want the beer, so I'd like something which had more common sense, more sense of realism. So I get the next model, and for example, that one I say, "Oh, get me a beer," and then I say, "Oh, well, forget it. I decided I didn't want it." And then I said, "But what are you doing?" He says, "I'm going into the kitchen." Well, why? Well, I don't know. I was going into the kitchen. Well, if you'd like to have some model for this kind of thing, this kind of notion of intention, what you have to do is relate this notion of intention to the beliefs, desires, knowledge, competence of the agents. And it would be fun to give a complete talk on their work, but Hector is here this year at Stanford, and I'm sure he'll give one. And so these are the kinds of things they did. They wanted to distinguish primitive events like lifting your hand from the notion of actions with perceived effects, like actually getting it to your mouth. Because you can try and lift your hand, but if there's something in the way. And what they really wanted to do is define a notion of relativized persistent goals, goals which you would have if you were an agent, but they wanted to put in some conditions which actually hadn't been considered very much when people were thinking about formalizing this. You want the condition that, for example, once something is done, then you don't want to do it again. Or if it's impossible, you don't want to continue to try and do it. And finally, you'd like to be able to have a general notion, if the background assumptions underlying the desire for this goal are no longer true, you'd like to stop having the goal. So that was part of what they did. And they've done a bunch of formal work on that. And this notion of commitment leads to another notion of commitment, which is a notion of interactive commitment. We won't go into that. Well, let me go to my last dimension, the one we have to think about how does this all fit in with the work practice. And it's too easy to think about systems and not really think about the roles that have to be played by the system and by the others there. You may not be able to see these people here who are the power source, what happened to the men it replaced. But that's not exactly the kind of systems that I think we want to build. The simple assumption is that it's sufficient to define abstract problems and solve them. We've seen lots of that in AI. And one of the things that and you see it in computer science and lots of places. And the problem is that you can solve these things, you can make them abstract and move them further and further, say this is a more interesting abstract problem, but it doesn't have enough to do with what's really out there. And this leads us to difficulties, One kind of difficulty is that we get things which people call NP-complete problems. Well, these are very hard problems because in the worst case, it's very difficult to do. For example, factoring is an NP hard problem. Except that in almost every case you can factor all the numbers. Half of them are divisible by 2. And then there's a third that anyway. So the issue is not whether something is NP complete, but what actually occurs in practice. And in the AI field, we very often say, well, what we're going to do is build an AI system which does something. And very often, AI technology alone is not enough to do these things. So that's kind of, I call that an AI complete problem. It comes from fighting the battle alone. There's lots of other technology out there. And solution complete, well, that's probably a bad terminology, but what I want to do is emphasize the notion that you really want to look at problems that use both the humans and the machines and the different kinds of computer technology in an appropriate way to solve problems. Let me give you some examples of use of AI in some interesting and different ways which are solutions to just part of the problem. So Ford has a problem. Ford has lots and lots of different models, and they all have different warranties, and the warranties keep changing. And every night, the dealers from all over the country send in and say, we have just fixed a car under warranty, and they have to check the rules to see whether they're going to pay those dealers back. Okay? And the way they had been doing it for a long time is they had a COBOL program. And every time there was a change in the rules, somebody had to rewrite a COBOL program and get it in. And they were getting further and further behind because the COBOL programmers couldn't actually do this very well to transform it. And they couldn't really tell whether they had it right. People would come to them and complain. And what they did is they started taking some of the most complex part of it, and they used a knowledge-based system where they could get a language which was very close to the language that the warranty administrator was using. And what that meant was that they could update things very rapidly because they could give a description of what they wanted in a language which was close to the statement in this thing built in a rule-based language. And what they've done is they started with the very hard ones, and then they increased. And what happened is, at that point, the warranty administrator said, hey, that's pretty good. I'll work with you directly now. I won't work through these programmers. And I'll start to understand how these rules work. So it was making a much better use. They had to leave the COBOL program. After all, it knew about all the communication, all the files, etc. Here's another example. This is one of my favorite examples. Mrs. Fields Cookies. As you probably know, Deborah Fields lives in Palo Alto and started with a little cookie shop down on University Avenue. But she, having been brought up here in Silicon Valley and having a husband who worked for IBM, so she had access to lots of technology, they've become one of the biggest users of technology there, and not just artificial intelligence. They have electronic mail and databases and spreadsheets which let them do most of the business processes they do. They have a full electronic mail system that connects all their franchises around the country, 200 and some odd of those. But in addition, they've built software, which they now sell, which answers questions like, how many cookies should I bake today? And it uses things like what the weather report is. It'll ask you, is it raining outside now? And what happened last year at this time? Should I give away free samples? That's my favorite one. I want to get into that program. But it depends on how long it's going to be until the next batch is out and how many you've sold. And you know, it really captures a lot of what Deborah Fields did when she was first starting out. They managed to capture this and make it available for the managers to be able to understand why these things work. They have something which is an advisor to how do you, what are the good questions to ask in an interview? I mean, it's hard enough to get people. How do you train people in interviewing so you get people who stay around for a while? I mean, after the second day of baking cookies, maybe it's not so much fun. You got to find the right people. And in fact, they are supposedly very successful at this. And part of what they've done is not only have these things there, but they have them as a glass box, as John Seely Brown would put it. They have programs which explain themselves, explain the reasoning they're going through. And of course, these programs interact with these databases, what happened this time last year. And electronic mail is a special going on right now. And what happens is they improve people's skills through the use of these things. Here's another example of combination of various kinds of knowledge. Gerhard Fischer and his companions at the University of Colorado were worrying about how can you help people doing design. And they had a domain which was design of kitchens. And they had two different systems. One of them was a system which you could read about all the issues in the design of systems on the basis of the issues that came up, like, well, small kitchens versus large kitchens, placement of various things, like should a stove go next to a refrigerator? And the answer is no, because the stove produces too much heat, except that if the kitchen is too small, and on the other hand. The problem with that one was that when people used it and then tried to design something, they forgot. And there was no way to get back to where they wanted to get. On the other hand, they built an expert system which, when you were working with this expert system, if you made a mistake, it would say, stove shouldn't be over there. And it would give you a simple explanation, like that heat one. But the problem was that then people didn't know very much more than what was there in the expert system. And what they did is they combined these two things, and it became much better. In both of the first two cases, people found it somewhat reasonable to learn about this. But when they combined them, so you had, here's a picture of from the advisor, and here it's just talking about, no, don't put those two things together. When you could combine these two systems, what it meant is that when you were doing the design, you would get a critique, and then if you wanted to get further understanding of the arguments, you could actually ask. And then you could be browsing through that thing, and then you'd need it at that time, so you'd remember it better. One final example, which is there just to say something about what happens when you get this thing into a very large organization. IBM has a very large manufacturing plant up in New Hampshire to make semiconductors. And they have lots and lots of expensive machines and some of the modern stuff, and it all comes with its own built-in computer systems. And they had lots of experts running each of the individual stations, and it was a mess. They really had a terrible time coordinating these things. They said, we felt data rich and information poor. And they put together this logistics management system, that's what LMS stands for, which dealt with some 240,000 transactions, things that were happening, interesting events a day. And they were able to combine operations research, statistics, all of this with knowledge-based systems to allow people to get better utilization out of the resources. So they were doing things like giving operators warnings when things were about to go wrong. They were talking about the schedule and trying to help them with the schedule. And the point was that this whole thing put together allowed people to get in there and control their own lives much better. And as they put it, it's not a cognitive replacement. It didn't replace anybody's job, but it augmented the ability of the people to do their own job. And they said no single expert can do what LMS could do. And it led to saving lots of money. I mean, this is one of the big success stories in AI. They won't tell us how many millions of dollars they save each year, but they admit it's in 6 or 7 figures. And that's measuring this thing fairly heavily in terms of productivity in their plant. And they said one of the interesting things that happened in the sociology there is the knowledge engineers who were working with them got to be experts on various parts of the system. But what was even more interesting from their point of view was the experts learned how to do knowledge engineering. That is, how to reformulate the knowledge they had as part of what they could do with their hands into ways that they could put it into the system and get the system to do part of the task. So it was really coming in and helping that whole system of people and machines work together. And so that leads me to the challenge that I think we face. I've seen too much in the AI literature, and I see it also in the various computing literature, of an us versus them mentality. We'll have an AI problem solver, and we'll have some big wall, and we'll define some thin interface. And then maybe we'll go over to a database. Or the database people say, well, we know about databases, we'll define some thin wall, et cetera. And I think we have to move our view. I think that kind of isolationist view is really bad for us. And what we have to do is we have to move up to kind of an interactive view. We have to go up to a view in which what we do is think about the various agents and worry about what is their common ground, how do they extend it. If they don't have a way of talking to each other, how do you make the impedance match better? How do you manage the resources in the system and let people know what the resources are in the system? How do you coordinate goals and actions? How do you integrate it with the work practice? And I think what we really want to do is come up to another level, a social and organizational view. We have to think about how the organizations interact with these things. We have to use information and knowledge from all of these areas. How does the way we account for what we're doing affect the way these systems work? Meg Graham, who's here, has a very interesting paper about how different accounting practices can lead to different ways of research organizations evolving. And finally, I think the point that we're trying to get at is that we really want to be supporting human values. We want to move people up the intellectual food chain. Unlike the kind of Taylorism that there was at the beginning of the 20th century, where the idea was to divide jobs up and make things as simple as possible and making the interfaces as narrow as possible. We want to move people up. We want to informate rather than automate. That is, get people to have the information they need. Get people to be higher up this intellectual food chain and distribute the knowledge and the power in ways that lets people really work well together. I think artificial intelligence and all of our different computer systems have to be an appropriate part of a kind of people and technology solution. We can't just focus on the one part. We have to constantly be looking out. And really what I'm saying is we want to build systems, that reflect and enhance the world we live in. Thank you. Happy to take any questions. It's late, I don't really want to. Yes?
What is your view of the current commercial approach to integrating AI and database systems together?
Well, I think that there are many approaches to integrating AI and database systems. And the ones which are trying to provide interfaces which make it easier for people to do things, which know about the structure of the databases, are going to be the ones that are actually going to succeed. And there are a number of systems which make it much easier for people to use the databases, not by knowing the facts that are in the database, but knowing about how to transform the queries in the language that the people have into queries in the language that the database understands.
You feel that the loose coupling between the systems I'm aware of, forget the particular commercial vendor, but the loose coupling between the AI system and the database is a concern, or you'd recommend all the users going through the AI system and the more convenient and not semantic-oriented interface it provides?
I think the issue here is what is the task you're trying to do. And so there's many different clients. And some clients will have to go through the raw database system. Some clients will use a different kind of mediation. You'll see lots of SQL interfaces. You'll see other clients which know about how to find things out in ways which, in fact, they cache lots of stuff. So I think the answer is going to be very task dependent.
I'll ask another question.
Yeah.
Have you used some of this technology? I believe you have a collaborative work environment going on here at Xerox. Perhaps you want to say more about that. How has this influenced that work, or vice versa? How has that work influenced this?
Well, you'll see lots of the work that's going on around here reflected in this talk. The work by Robertson, Card, and McKinley was one example in which the cognitive coprocessor was there. The work by Huberman and company is another example of analysis that's going on here. The work on reification and understanding how to use those objects is the focus of a lot of different kinds of work in the embedded computation area around here. So there's lots of work that's going on here that's using these kinds of models. And one of the things that's very exciting about Xerox is that there's lots of different, not just technologies, but sciences represented here. And so we use input from anthropology, from sociology, from linguistics, et cetera, to try and help us form the models that we're going to use. Yes?
What systems in use around CSL or EL or SSL use AI techniques?
What systems in use? Well, I mean, we have available to us some of the commercial systems, but it's actually an interesting question about how do we use these things in our day-to-day lives. And we have used some of these in our day-to-day lives. The CoLab. What? And its interface, right. I mean, there's AI technology that has been used in the design of some of these systems, like the user interface. There's some of